Hey guys, this is the fourth and final part of the AQA Further Maths GCSE Paper 2 from June 2017. So we're kicking off at question 21 and we're finishing the paper. So question 21, we've got a sketch of the graph of y equals x plus 2 times 4 minus x. We're told the graph intersects the axes at A, minus 2, 0, B, 4, 0, and C. So C is the y-intercept. Part A asks us to work out the coordinates of C. So, on the y-axis, x is equal to 0. So we know the x-coordinate is 0. If we then substitute that into the equation, we get y is 0 plus 2 is 2 times 4 minus 0, which is 4. So we got 2 times 4, so we get y is equal to 8. So our coordinates of C are 0, 8. Lovely jubbly. Part B asks us to work out the gradient function of the curve. So to be able to work out the gradient function, which is dy by dx, we need first of all to expand the brackets. We could do it without, but that's trickier differentiation. So let's expand the brackets. So we've got x plus 2 times 4 minus x. If we expand that out, we are going to get minus x squared. We're going to get minus x times positive 2, which is minus 2x. And we're going to get x times 4, which is positive 4x. So we're going to get plus 2x. And then we're going to get 2 times 4 at the end, which is 8. So that's our function y. We now need to find our gradient function, which is dy over dx. So we're differentiating minus x squared, and the power of 2 comes down and multiplies, and the power goes down by 1. So we get minus 2x like that, and then 2x differentiated is just 2. So our gradient function is minus 2x plus 2. Okay, and then for part C, we are told the normal to the curve at C intersects the x-axis at point Q. We want to show that length BD is twice the length of AB. So, let's first of all go back to the diagram. Work out the length AB. So, length AB is taking us from minus 2 up to 4. That has a length of 6. So, AB is 6. So, a normal is the line perpendicular to a tangent or perpendicular to a curve at a given point. So what we need to do here first of all is work out the gradient of the curve at point C. So gradient at C, well, we know our gradient function is minus 2x plus 2. Now we know at C, we know that x is equal to 0. So if we substitute that in, we're going to get minus 2 times 0 plus 2. So the gradient of the curve at C is 2. Now, we also know with perpendicular lines that gradients multiply together to give us minus 1. So then we know 2 times the gradient of our normal is equal to minus 1. So if we divide by 2, we then get the gradient of our normal is equal to minus 1 over 2 minus 1 half. If we then stick that into y equals mx plus c, we get y is minus 1 half x plus our constant c. Now we need to find the value of c, so let's see, we're at point C where we know that x is equal to 0 and y is equal to 8. So that actually tells us that c is equal to 8. Okay, so the equation of our normal is y equals minus 1 half x plus 8. Now, we want to find the point where this line crosses the x-axis. Everywhere on the x-axis, y is equal to 0. So, we substitute in y equals 0. So we get 0 is 1 half x, minus 1 half x plus 8. If we add our 1 half x, 1 half x is equal to 8. Therefore, x is equal to 16. So our normal intersects the x-axis at x equals 16. So that's going to be over here somewhere. Point D has coordinate 16, 0. Now length B to D is then going to be 16, take away 4, which is 12. So remember what we were trying to show is that BD is 2 lots of AB. So BD is 12, AB is 6. 12 is 2 times 6. We've shown what we wanted to show. Jobs again. Okay, next up we have the equation of a circle is x minus 2 squared plus y minus 1 squared equals 16. We also know the equation of a line is y equals 2x plus 1. We are told the circle and the line intersect at 2 points. We want to find the coordinates of these 2 points. So, how are we going to do this? Good question. We're going to use substitution. So, we use the linear equation as a substitution into the equation of the circle. So, we no longer think of y as y, we think of y as 2x plus 1. So, the equation of our circle then is going to become x minus 2 squared plus, well, we had y minus 1 squared. We're now saying that y is 2x plus 1. So, we're going to get 2x plus 1 minus 1 squared, and that's equal to 16. So, we've got x minus 2 squared plus, just 2x squared. That's nice, which is equal to 16. If we then expand our brackets, x minus 2 squared gives us x squared minus 4x plus 4, and then 2x all squared gives us 4x squared. That's equal to 16. If we then sharpen things up, we've got x squared plus 4x squared, which is going to give us 5x squared, and then we've got minus 4x. Now this chart is a quadratic, so we're going to have to solve this quadratic, so we want everything on the same side, with a nice 0 on the right hand side. So we're going to take away the 16, so 4 minus 16 is minus 12. So that is equal to 0. Now look, can we factorise this guy? Good question. Let's have a go. So we've got 5x squared in one bracket. We're going to need a 5x. In the other bracket, we're going to need a single x. So we've got a minus 12 at the end. That means one of our numbers is going to be positive. One of our numbers is going to be negative. We got a minus 4 in the middle. So what numbers multiply together to give us 12? We've got 1 and 12, 2 and 6, and 3 and 4. So I think I've just spotted the solution. If we stick a minus 2 in there, then we're going to need a plus 6 in there. So minus 2 times 5x would give us minus 10x. Positive 6 times x gives us positive 6. So minus 10x plus 6x gives us our minus 4x in the middle. So that is indeed factorised correctly. If you want a nice method to factorise harder quadratics, check out my video called Factorising Harder Quadratics. It's really useful, it always works. As long as your quadratic can be factorised, it always works. So that might be worth checking out. So we now want to solve this to get our two x coordinates. Let's change colour. Everything's getting a bit blue. Let's go for red. Okay. So the right hand bracket tells us x is equal to 2. What about this guy on the left though? So we set whatever is inside each bracket equal to 0. So 5x plus 6 is equal to 0. Take away the 6. 5x equals minus 6. Divide by 5. X equals minus 6 fifths or minus 1.2. So, what we've got so far are our two x coordinates. Now we need to work out each y coordinate. So to do that, there's good news. We've done all the tricky stuff. We now just use y equals 2x plus 1 with each of our x coordinates. So let's change colour again because we're doing something different. Okay, so y equals 2x plus 1. Well, when x equals minus 1.2, then y is 2 times minus 1.2, so minus 2.4 plus 1, which is minus 1.4. So one of our sets of solutions is x is minus 1.2, y is minus 1.4. And our other one then is when x is equal to 2. Well, for that then, y would be 2 times 2 plus 1, which would be 5. So our other set of coordinates is 2, 5. Quite happy I managed to do that all in one take without messing up. Okay, question 23. So some trig identity fun. So in this question, tan of x and sine of x are not equal to 0, which is important. Otherwise we'd be dividing by 0, and that's naughty. We want to show that 1 over tan squared x minus 1 over sine squared x is a constant. So just a number with no trig nonsense kicking around. Okay, well, first of all, we need to remember tan of x is sine of x over cos of x, and we're probably also going to need sine squared x plus cos squared x is equal to 1. So, let's deal with 1 over tan squared x first of all. So, 1 over tan squared x. Well, that's saying 1 divided by tan squared x, which is saying 1 divided by sine squared over cos squared x. So when you divide by a fraction, you flip it over and multiply by the bugger. So this is going to become actually just cos squared x over sine squared x. So now our question becomes cos squared x over sine squared x minus, is it minus? It is minus, good times, minus 1 over sine squared x. Now we've got a common denominator here, so we can actually just combine this and say that it's cos squared minus 1, cos squared x minus 1, I should say, over sine squared x. So from that we can rearrange cos squared minus 1 is minus sine squared. If we rearrange this guy up here to get cos squared minus 1, we would have to take away sine squared, so we get cos squared is 1 minus sine squared of x. So then if we take away the 1, cos squared of x minus 1 is minus sine squared of x. So we've got cos squared minus 1 on top of our fraction here. So we've actually got minus sine squared x over sine squared x, which is indeed minus 1, which is a constant, as we wanted to show. Jobs again. Okay, question 24, the big finale. We want to write 12x squared minus 60x plus 5 in the form a lots of bx plus c all squared plus d. So that is completed square form, and we need a, b, c and d all to be integers. Good times. So probably a good idea to arm yourself with a calculator for this one. I'm going to try and do it without. We need to end up with integers, so the numbers should work out alright, maybe. So, right then, 5 marks for this bad boy. Let's do this, we're not scared. I'm a little bit scared. So, the first problem is we can't complete the square until we have a single positive x squared term. So at the moment this 12 is a right pain in the ass. So to get rid of that, we can't just get rid of it. What we can do though is move it by factorising 12 out of the whole expression. So we can write this as 12 lots of x squared minus 60x divided by 12 is minus 5x, and then 5 divided by 12 is 5 twelfths. I like that. Good times. Okay, so inside of the big square brackets, we do now have a single x squared term, so we can now complete the square. It's not going to be very nice, there's going to be lots of fractions. Just take your time, take it slow, don't rush. So, on the outside then, you got 12. Now, to complete the square, we want a set of round brackets with a single x on the inside, a square on the outside. We're going to keep this 5 twelfths on the outside 4 now. It's not going to stay there. Now we need to half minus 5. Half of minus 5, just have it as a fraction. Half of minus 5 is minus 5 over 2. Now, the final step here is we need to square 5 over 2 and then take that away on the outside. Now 5 over 2 squared is 25 over 4. So we take that away on the outside like that. A lot of people here would go, what? We've got a minus number inside the bracket. Surely we add that on. Never ever add a number on the outside. Always square that number inside the bracket, which is always going to give you a positive number, even if it's positive or negative. It's always going to give you a positive. So you then need to counter that out by subtracting it on the outside. Okay, so we're going good, guys. So we've now got 12 lots of x minus 5 over 2 squared. Now you can just use your calculator here to combine 5 twelfths minus 25 over 4. I'm going to do it without though, because I don't like calculators. So we've got 5 twelfths. Now we need to turn 25 quarters into twelfths. So we do that by multiplying the top and bottom by 3. So we then got minus 75 twelfths, like that. So we then got 12 lots of x minus 5 halves all squared. Now 5 twelfths minus 75 twelfths, it's going to give us minus 70 twelfths, like that. So, we've done it. All we now need to do is let our 12 back in. So our answer is 12 lots of x minus 5 over 2 squared. Now 12 times minus 70 over 12 is minus 70. Okay, so this is incomplete square form, we're almost there. There is one problem though. We've got this minus 5 over 2, which is not an integer. So we wanted A, B, C and D to be integers. So how are we going to get around this? Well, what we're going to do, we're going to turn x minus 5 over 2 into a single term. We'll do that over here first of all. So we've got x minus 5 over 2. So how can we turn that into a single fraction? Let's think about this in terms of common denominators. Multiply x by 2 over 2, then we get 2x over 2 minus 5 over 2. So we get 2x minus 5 all over 2. So we can write this stuff inside of that bracket as that. So we've got 12 lots of 2x minus 5 all over 2, like that. Now that is all being squared. And then we've got this minus 70 on the outside. Now, when you square a fraction, you square the top and square the bottom. So, we could actually say this is 12 lots of 2x minus 5 squared over 2 squared, which is over 4 then, like that. So this 4 can escape out of the bracket because it's dividing, it's dividing everything in the bracket by 4, so it can divide that 12 out of the front by 4. So then we got minus 70 on the outside like that. So finally, we can now divide the 12 by that 4, and we've got 3 lots of 2x minus 5 squared minus 70. So that was an extremely tricky completing the square question. A cheeky little bit of algebra manipulation there. But good news, we finished the paper. So, closing thoughts, I would certainly say paper 2 was a lot harder than paper 1. For a start, it took 4 videos, so that's probably a good little sign that it's a lot harder. It seems to me like most people out there haven't really been taught further maths that have been put in for the exams. It's just kind of last-ditch effort just to get another GCSE, which, why not? So, if you haven't been taught it, lots of stuff's in there. Lots of stuff in here is going to be so tricky. So don't worry about it too much. Ella and Kaya, if you're watching this and you've made it this far, I imagine by now we've had our final lesson. So once again, a massive good luck to you guys for this exam. Same for the Kill ladies. If you're watching this, very good luck to you guys. Hi, Caden. Just a massive good luck to everyone. Take it easy. Don't panic. Do what you can do. If you get another GCSE, ideal. If not, no great loss. Take it easy, guys. Take care.